Okay, so the main idea is this orthocenter reflections. And so it goes like this. You have triangle ABC, and um, you have the orthocenter H, and yeah, basically there are two ways you can reflect the orthocenter. So here's one. So this is a reflection about the foot of the altitude. So it's if this is D, then HA is oh, that's not right. HA is the reflection of um, H over D. Um, and then the other reflection is this one. So you can take, let's say, the midpoint M. Uh, so this is, and the other reflection you can take is here. Okay. Um, we can call it HA prime over um, over M. And so the claim is, HA and HA prime are on the circumcircle. Okay. So have you guys seen this reflection lemma before?
Yeah.
Yeah. Yeah. Okay. So maybe I won't spend too much time, but okay. The point is, okay, this is I mean, the proof is simple. You just calculate these angles, right? So both of these angles will be equal to this one, and okay, then you can calculate, and it'll be 180 minus A. So okay. So the angle is 180 minus angle A. Okay. So that's how the proof goes. Um, okay, great. So this is some pretty common um, lemma. So how is it used? So we're going to recall this is the problem we were working on last time. Um, now, how does this problem work? Yeah, so let's recall. Um, you started with triangle ABC, and then there was this point K. So given was triangle ABC, and then you have uh, with K on the circumcircle. Um, between B and C, right? Um, and then you have uh, L and M. Okay, so L and M are reflections of K over AB and BC. Okay, and then what do we do? And then Um, so then, yeah, so it's not, I guess it's not drawn here, but then we took, um, then we took, that's right, so we took circumcircle. So it's not drawn in this picture, but we took the circumcircle of BLM. So that's this guy. We take this circle here, and we constructed this point E. Okay, so so this point E was the intersection of the circumcircle of BLM with the circumcircle of ABC. Okay, so circumcircle of BLM intersects um, the circumcircle of ABC at E. Okay. Um, and then the problem was to show, so the problem show that EM and KH concur, um, sorry, intersect, let's say, on BC. So that was the problem that we were trying to solve. Um, yeah, so we wanted this EM and this KH to intersect on BC. Okay, so that was the problem. And so we did a couple of simplifications. So the first simplification we did was, um, so first, yes, first we constructed this HA. Uh, so first we constructed this HA here, which is, as before, it's the reflection of H over BC. Um, so it's this H and HA are reflections over BC. And then what we observed is that, okay, so K and M are related by reflection, and H and HA are related by reflection. So actually, these two, KH and MHA, already intersect on BC. So the very first reduction was that you can actually reduce the problem to, um, instead of showing that like uh, that E and M, EM, BC, and HK all intersect, you can reduce to showing that E, M, and HA are collinear, right? So the problem, the very first reduction we made is that this problem is equivalent to showing that E, M, and HA are collinear. So are there any questions about that first reduction? So that this E is not, it's not this E prime. It's really the intersection of the circle of BLM and ABC. Yes. So before I continue, I want to make sense. So does it make sense what I've written? That the problem is equivalent to showing that E, M, and HA are collinear.
Which point?
So the problem, what we're trying to show, is equivalent to showing that this statement, that E, M, and HA are collinear. Does it make sense what I'm saying?
Um, I don't get how they would be collinear.
Um, no, so I haven't shown that they're collinear. I'm saying that the problem statement is equivalent. So if we could show that they're collinear, then we've solved the problem. I'm not claiming yet that they're collinear. Does it make sense what I'm saying? Okay, I'm working backwards. So I'm working from the problem statement, and I'm saying that uh, so what I'm saying is that this and this are equivalent statements. Okay, maybe I can draw it again. So um, um, okay, so um, maybe I can take a slightly simplified picture. So yeah, okay, let's yeah, let's maybe take this picture. So here's the picture, and what we've added is we've added HA, right? So okay, and so the first observation is that okay, so what we want to show is that EM and HK intersect on BC. So the observation is that HK and MHA intersect on BC. Okay, so therefore, the problem statement, so by the problem statement, I mean what we want to show, so these two things, is equivalent to showing E, M, H, A are collinear. Okay, does that make sense now?
Yeah.
Okay, good. So instead of showing this concurrence, we're showing this collinearity between these guys. Uh, um, so Abdullah, does that make sense to you as well?
Yeah, all right.
Yeah. Okay. So now the second thing we said is okay. So um, instead of showing this collinearity, what you can do instead is the following. You can um, and so instead, what you can do is um, yeah, maybe I need some more space. Instead, let E prime be the intersection of MHA and the circumcircle of ABC, and then show um, BLME prime concyclic. Okay, so what I'm saying, so instead of showing that these are collinear, So it's yeah. So of showing that E, M, and HA are collinear, you construct this this point E prime. Um, so you take MHA and you let it intersect at E prime, and then you show that BLM and E prime are concyclic.
Yeah, that's clear.
Okay, and so that brings us now. Okay, so this I guess what we covered last time. So that brings us to um, the present situation here, right? So here, what do we have? we have this HA, and then from HA we've constructed from HA we've constructed E prime by intersecting with the circumcircle, and our goal now is to show that so yeah, so what is our goal? Our goal we've reformulated the problem to showing that B, L, M, and E prime are concyclic. Okay. Um, so that's so are we all on the same page? Does it make sense?
Yeah.
Okay, so how do we do this? The yeah, so there's okay. So what is now there's another very clever observation you have to make, um, which is the following. Um, it's that if you now take the orthocenter, so we yeah, so what happened? We took the orthocenter and we reflected over BC to get HA. And now if you take the other reflection um, over AB and get HC. And now it's I guess it's not obvious, but there's a observation. Maybe you have to yeah. So there's an observation that these three um, look collinear, and in fact they are. Okay. Um, okay. Maybe let me give some motivation why you might ever consider this HC. The reason is because okay, how did we get? We started with K. That was the very first point we constructed. And then from K, we got M and L by reflecting over BC and AB. Okay, so maybe it might be natural to take H and reflect over BC and AB, and then they get those. Um, yeah. So, um, so the rest of the solution goes basically in two steps. So the first step is to show that these 3 points that look collinear actually are collinear. And then we use that fact to prove that BLM and E prime are concyclic. Okay, so let's do this. Uh, so so first, let's sure. Okay, yeah. So remember, this is what we want at the end of the day, that BLM and E prime are concyclic. Um, and yeah, so let's now erase all of this. Okay, so right. Um, so the first claim, claim one, is that uh, L, H, C, and E are collinear. Okay, E prime rather. Okay, And let's just remember, how did we get these points? So um, we right. So the way we got these points was, well, so one of them is you take H and then you reflect HA, and that gives you E prime when you okay, no, sorry. Yeah, that's right. So that's right. You take H and you get HA, and then from K you get M and L, and then from HA and M you get E prime. Right. That's the idea. Um, okay, so any ideas how we can prove this? So somehow we basically have to reduce this to some kind of angle equality. Okay. Maybe I'll give yeah, so do you guys understand what we're trying to show now, right? This is the first, there'll be two steps to the solution. First is to show that these are collinear, and then to show that the BLME prime are concyclic.
Yeah.
Okay. Yeah, so maybe give some time to think how we might prove this. But basically, whenever you're trying to prove that three things are collinear, right? If you um yeah, like the most straightforward way without like using some technique is to show that like two angles are the same, right? So like um you know, like that this angle and this angle are the same. Okay, something like that. Um, some comment which is okay. You can think about this for some time, but the angle equality you end up wanting to show is this. So maybe I'll just draw it in. You draw in this guy here, and so the proof will go by like this. It will go by showing that angle LHCB is equal to angle um, uh, right. So okay, maybe there's two ways of doing this. You can write it as either 180 minus angle E prime HCB. Okay. Um, yeah, so basically, uh, so basically, uh, this angle and this angle. But the more maybe scientific way is to use directed angles. So if you use directed angles, what you're showing is that um, uh, LHCB equals the directed angle E prime HCB. But okay, if you don't know if you don't know what directed angles are, don't worry about it. But if you do, then okay, this is the more scientific statement. Okay, regardless, you want to show that these two angles here, um, this one and this one, are supplementary. Okay, so let's see if we can calculate these by some kind of angle chase. And remember, like these points all came from some reflection. So sometimes it's easier to reflect them and then calculate the angle. Yeah, maybe I'll. That's any ideas? Um, so maybe I can mark some angles. Uh, so let's make the small one blue and the big one red. So I'll mark this in blue and then this one in red. So so one place you can start is this blue one. Um, uh, so uh, L and HC are both reflections, right? And the reflections of K and H, right? So what am I saying? I'm saying L and HC are reflections of K and H over AB. So actually, that tells you that this blue angle is also equal to this angle here. The first, oh, it disappeared. This angle there. So first you can start by saying angle LHCB is equal to um, BHK. Does that make sense? This is by reflection over AB. Does that make sense? If for some reason I can't hear your microphone clearly. Um, okay. But okay, I think it's okay. So now let's, and then what? And then well, so that was by reflection over AB, but now you can actually go one step further, right? So now um this H and K themselves are also reflections, right? So if you look at H and K, remember at the very beginning we observed these are reflections of M and HA, right? So if you take H and the K and you reflect over BC, you have M and HA. So you can actually go further and you can say that BHK is the same as this angle here. So you take yeah, so I'm gonna consider this guy and I take this angle. Okay. Um, so BHK is the same as um, BHK is the same as let's say MHAB. And this one is by reflection over BC. Yeah. Okay, but now at this point we're done, right? Because what we've now um, this blue angle, this new blue angle here, is just supplementary to this red angle because there's a cyclic quadrilateral, right? So, and then we say, okay, so then, but angle MHA, or MHAB plus angle E prime HCB equals 180 degrees uh, by cyclic quadrilateral. Okay, so then that proves that proves collinearity. Yeah. Does that yeah? So does that make sense to everyone?
I don't get how we got MHAB.
Um, so is it this line here?
Uh,
Primoria.
yeah,
Yeah. So the argument is we were trying to calculate BHK, right? BHK. So H and K are if you reflect them over BC, K becomes M and H becomes HA. So I'm saying this angle here, BHK, and then BHAM, they're
okay, I
reflections over
get
BC.
it.
Okay, good.
Yeah.
So that's this one here. So the whole thing went by reflections, right? We started with this angle. We reflected it to get this angle, and then we reflected again to get this angle. Yeah. So does it make sense now?
Yes.
Okay. Yeah. So that's the full argument for collinearity. Um, okay. Um, and now what's next? So then and then well, by the way, Abdullah, does the argument make sense as well?
Yeah, it's fine.
Okay. So now the second part is how do we use this collinearity to solve to finish the problem, right? So remember, this is our goal, that BL, E prime are concyclic. So I think we'll need a new page for that. So let's give a new page. Uh, yeah. So we have collinearity now. So now let's do claim 2, which finishes the problem, which is that BLM E prime are concyclic. So let's see, how can we do this? So again, concyclicity is some kind of angle condition. So let's see, let's think which angle condition might be easier to work with. Um, so I think, yeah, I think the one that might be the easiest to work with is, I'll erase this now, we don't need this anymore. Is That's right. So the one that should be the easiest to work with, I think, is this one. So this angle compared to this angle. Okay. Um, yeah, so we'll show what we want to show is that angle LBM is equal to 180 minus angle uh, L E prime M. And okay, again, I'll make the point that if you were using directed angles, which you should if you want to avoid configuration issues, is what you would show as LBM is the same as the directed angle of LE prime M. Okay, if you use directed angles, which you should, but okay, anyways, I won't bother about that right now. So why I think are these two angles good to compare? So one is that, okay, if we look at L E prime M, we get to use that we get to use this collinearity result because instead you can do HC E prime M, right? So yeah, so maybe I'll just make that comment, which is that uh, this angle is also HC E prime M because of the collinearity that we showed. And then the other point is actually you can calculate LBM. Okay. And why can you calculate LBM? Because just think about what the situation is. It's a kind of a so we had K, which we reflected to get M and L. So if you look at these three things, sorry, yeah, so it's this one, and this one. So the point is you actually know all of these angles. Um, Yeah, you can calculate all of these angles because of the reflection properties, and so actually calculating LBM is not so hard. So let's do it. Um, uh, so how do we phrase this? We say um, uh, yeah, we say LBM is it's LBK minus MBK, and then because of the reflection, these are just double angles. So LBK is twice ABK minus twice so yeah, so LBK is twice ABK and MBK is twice CBK. And so that becomes twice of ABK minus CBK, which is twice ABC. Okay. Does this calculation make sense?
Yeah.
Okay, so I've just used the reflection property here. So that's LBM. We really have a good idea what LBM is, and now let's see uh, if we can calculate this other angle. So this is LE prime M, which we know is HC E prime M. So what can we do with HCE prime M? Um, well, um, mm, yeah, so this one, uh, oh, sorry. Yeah, let's actually not write it as HCE prime M and write it as HCE prime HA. I think that's better. Uh, right. This guy is equal to HCE prime HA. Uh, um, um, and now this is a little bit easier to work with because what we realize, what are we really doing? We're calculating some arc here, right? This is some kind of arc on a circle, so there's a lot of information we have. Um, yeah, so I think the easiest way to finish the calculation will be to notice like this, that yeah, so this guy is supplementary to this guy. Um, so this is 180 minus um, HCBHA. And then the point is, well, uh, how did we get HC and HA? Well, we just reflected H over two sides. So it's again some kind of double thing, right? So this is 180 degrees minus. So what do we subtract? We do, well, right, so HCBHA is HCBH plus H plus HBHA, and those are both double angles. This is 180 degrees minus twice um, uh, minus twice uh, ABH plus twice HBC. Okay, and then we're done, right? Because those two angles add up to angle ABC. So does it make sense?
Yeah, yes.
Okay, so any questions about this problem? Uh, so maybe I'll ask one thing, which is kind of a strategy problem, right? So let's say we got to this point here, where we know we have to show that B, L, M, and E prime are concyclic. So we've arrived here. So my question is, how might you consider that you want to construct HC, right? Like maybe HA was kind of natural to construct because of this whole thing, but how might you know to construct HC? Do you guys understand the question that I'm asking?
I guess, yeah.
So I'm asking like a strategy level question, which is, how do you know to construct the sky? Okay, so one way you can sort of arrive at constructing HC is you can say, look, I want to show that these 4 points are concyclic. I can calculate this angle. So you have to basically observe that you can calculate this angle. LBM. And you might observe this just because of, I mean, the construction of LBM is pretty sort of simple. You start with K and then you just reflect it twice. So since you know you can calculate this angle, a natural way to show consequently is to show that now I have to calculate this angle. Um, but now I know that E and E prime M and HA are collinear, so I want to basically, what I'm saying is calculating this angle is the same as identifying exactly where on the circle this intersection point is. So let me write it out a little bit more. Um, so what I'm saying is um, to calculate angle L E prime HA, you want to know where LE prime intersects the circumcircle of ABC. Okay. Um, yeah, you want to know exactly like, say for example, what this arc length or like what this arc length is. Okay. So because my point is because LBM is a known angle, right? Since that guy is known to be what is it? Like it's like since you know that this angle is twice I think beta, right? And so you want to show that this is 180 minus twice beta. You can calculate exactly what you need these arcs to be. So what that tells you is that this point is some kind of known point. Okay. And so if you go through that calculation, what you'll find is that this arc has to be something like 90 minus alpha, and this arc has to be something like 90 minus beta. Okay. And okay. If you've looked at these diagrams enough, you'll know that that's exactly the location of this point. Does it make sense what I'm saying?
Uh, I think, yeah.
But what I'm saying is even if you didn't know to draw HC, you could have figured it out by identifying what this intersection point had to be. Okay. Does that make sense?
Uh, yeah.
Okay. So I didn't solve it that way because I didn't want to have the reasoning be too like weird, but I think that's how you would have solved this problem. Um, okay. Uh, okay. So now now I want to do another problem. So this is yeah, so it's going to be more reflections on this theme of orthocenter reflection. Oh, I didn't mean to make a pun, but yeah, it'll be more problems related to this theme of orthocenter reflection. So what's the problem? So this is from the homework. It's oh no, this is actually not from the homework. Okay, this is not from the homework. Um, but let's try it anyway. So um, it goes like this. Uh, so this is from ISL. This is the IMO shortlist 2000. So let O be the circumcenter and H be the orthocenter of acute triangle ABC. Okay, and then the problem is show that there are points D, E, F on sides BC, CA, and AB such that the following is true. OD plus DH equals OE plus EH equals OF plus FH, and AD, BE, CF are concurrent. Okay. Um, yeah, so let's draw a picture first. Um, okay, so first I'll draw a bad picture and then we'll draw a good picture. So uh, let's see. Usually I draw the circle first because it's easier. Um, so there's ABC, um, there's O. Okay, and then there's H. So there's H, and then I won't label it. It's a lot of. So now what? Now we want D, um, E, and F in such a way that uh, each of these sums is the same. Okay, so want, yeah, it's already written here, so right. So this is OD plus OH. This is OE plus OH, and this one is uh, OF plus FH. Oh, no, sorry, I drew the wrong thing. Yeah, that's right. One of these is wrong. This one, OF plus FH. Okay, so does the problem make sense? Do you guys understand the problem? Hello?
Yes, I do understand the problem.
Okay. So, yeah, so any ideas how to proceed? So whenever you see H and the circumcircle, you should always do the same thing. You should take this H and you should reflect it. Um, so if we draw the reflections, okay, Yeah, so any idea what this gives us? Yeah, so the idea here is, if you if you draw the reflections, you can actually get a good guess of what D, E, and F are supposed to be. So the point here is that once I do the reflection, HD is the same thing as HAD, right? So each of all of these lengths, you can actually just instead of taking the distance from like DE or F to H, you can take it to the reflection, right? So what you want is that DHA plus DO equals um, EHB plus EO which equals FHC plus FO. That's what you want, right? So what is there a natural DE and F that makes this true? So maybe I'll give some time to think about this. So
Um, maybe you could try the intersection of HA and HAO and BC and the other stuff.
of HAO and BC.
Yeah, you'll
That's right.
have they will all be equal to the radius.
That's right. So if we take this right, that's right. We do this. We do this point here. We take HAO and we intersect with BC, and that's right. So that's actually that's the key idea here. Yeah, so the idea is you want to make I don't have, maybe I can write it here, is D is yeah, so that's right. The idea is D should be HAO intersect BC, and then E should be HBO intersect AC, and F should be HCO intersect AB. And then if we do it like this, then these are all equal to the circumradius. Okay. Yeah, so that's a very natural guess. So what we have to do from there is we need to actually show that for those choice of DEF, these are concurrent. Okay. Um, so let's draw the situation we have then. It's here. That becomes the situation. So, right, so yeah, so D, E, and F are the intersections of this HAO and BC, right? So now what do we want to show? I want to show um, AD, BE, CF concurrent. Okay. Um, so this kind of concurrency is okay. Yeah, so whenever you have this kind of a concurrency where I have like uh these are called Chavians. That's what they're called. Yeah, so these kinds of things are called Chavians. And so it's trying to show some kind of Chavian concurrency. So
Yeah,
and
I said the theorem.
okay, great. Yeah, so like almost always what you want to use is Chavis theorem, right? Um, so what do we need to know? We need to know for Chavis theorem, we need to know BD over DC. What is this equal to? Um, yeah, so any idea how to calculate that in this case? Yeah, for the theorem, you need BD over DC times CE over EA times AF over FB, but okay, we can just calculate one and we'll be done. Yeah, so maybe I'll give some time to think about this, but you should know how to calculate ratios like this. It's yeah, the usually the idea is um, yeah, usually the idea is you either calculate some kind of area ratio, or even more simply, if I have a triangle like this, and I draw this thing here, how do I calculate the ratio between between this and this? One very common way you use is you say, well, I can calculate something with these angles, right? So it's if you can calculate these four angles, then you can calculate the ratio using law of sines. Um, do you guys know how to do this calculation? If I know this angle, this angle, this angle, and this angle, then I know the ratio.
Uh, I think, um, yeah, um, can we just name the angles?
So it's ABCX. And let's
Okay, so,
so this is beta, gamma, and let's say then little x and little y.
yeah, so, dx divided by sine of dAx equals, um, ax divided by sine of abx, and we do the same the opposite side.
That's right.
Cx divided by sine of Cax equals Ax divided by sine of gamma.
That's right. So then we get bx over cx is equal to sine x over sine beta time. Okay, maybe they need some more space. Okay, so what's the maybe let's write the conclusion in red. So it's bx over cx is equal to sine x over sine beta times um, sine gamma over sine y. Okay. Okay, great. So if we do it in this picture, that won't work exactly because I don't think it's easy to calculate these two angles. But there's a better triangle you can use. So let's see if we can find it. There's a triangle you can use in this picture to calculate this using this method. So we just need a triangle where yeah, to pick what, so it's A will, if you do A, B, C, it's too hard, but you can use some other point other than A.
Can we use O?
Yeah, so if you, yeah, what happens if you use O? Um,
Yeah, we get Vx divided by C. X is equal to, or
so
yeah, but we get an isosceles triangle.
yeah, it's isosceles. I'm not sure I know these angles though. Um, wait, maybe we do. Oh, you're right. We do actually know these. You're right. You're right. We know these angles. Why do we know these angles? Because um, they're just these arcs, right? And what are these arcs? They're that's right. Yeah. So yeah. What's the idea? So um, yeah, you definitely know these angles. So uh, this this angle this angle is twice of this angle, right? Did you see it? Does it make sense?
Oh yeah.
Right. So yeah, you do because yeah, I mean the main point is this is some kind of oops blue. So maybe I'll just use the highlighter. So this angle, whatever it is, you should always be able to calculate this angle because it's an arc between 2 points that you know, right? B is a point of the triangle and HA is a you know where that point is basically, right? Um, so um, yeah, okay. So maybe I should draw it a little bit better. So but the point is this goes through H. Right? So it's this angle. Um, yeah. So let's just fill in the picture here. So um, for us, X, this angle X, which is blue, is uh, twice um, twice 90 minus angle B. So this is 180 minus twice angle B. Um, and then Y is 180 minus twice angle C. And then what are beta and gamma? So beta is, well, beta and gamma are the same in this case, so we actually don't care, right? Does that make sense?
Yeah.
Yeah, so actually it's very simple, I think, right? It's just sine of 180 minus twice angle B over sine of 180 minus twice angle C, which is sine of twice B over twice C. Okay, and so now it's I mean, okay, this is some kind of cyclic product and it'll be equal to 1. Does it make sense?
Yeah.
Okay, good. So that's yeah, so that's a very it's a very clean solution. Um yeah, so I think I said it before, but this was this problem was from the IMO shortlist 2000. It was G3. So it's the difficulty of a problem 1 or problem 2. Um, okay, so any questions or comments on this?
No.
So one thing I wanted to maybe review one time. Have you guys seen the proof? Do you guys know about this 9-point circle? Have you seen the proof of this?
No.
Okay, so let's look at the 9-point circle. So this is a very nice configuration. So again, it uses this reflection thing, but it uses it very cleverly. So let's find the picture. So where is it? It's here. So this is called a 9-point circle. So it's a circle with 9 points on it. What are the points? So the points are um they're the so they're the yeah, so we have H here. So these are the feet of the altitudes. Maybe we call these D, E, and F. Um, these are the feet of the altitudes. And then there's also these 3 points. These are the midpoints of the sides. So I'll call them maybe K, L, M. So K, L, M are the midpoints of BC, AC, AB. Maybe BC, yeah, sure. BC, AC, and AB. And then the other ones are not, then the other 3 points are not so interesting. It's these. And what are these? These are so the red ones are the midpoints of AH, BH, CH. So they're the midpoints of a segment of the altitude. Okay, and so the 9-point circle theorem is that these 9 points are on a circle. Okay, so does the statement of the 9-point circle theorem make sense? This is this the statement.
Okay, but how can I prove?
Yeah, so yeah, the proof is you have to use this orthocenter reflection guy, right? So what is this say? So we have HA here, no,
Oh, I
that's
mean, I think I get it.
yeah, so maybe you can explain how this works.
Um, actually, no.
Yeah, so yeah, I mean the thing is consider this guy, right? So consider a dilation centered at H with factor 2. This is the key idea. Um, um, so what what happens to these 9 points when you dilate them centered at H with factor 2? So the point is the blue guys, D, E, and F, when you dilate by a factor of 2 will become these HA, HB, and HC. Does that make sense? So the first claim I'm saying is that under this dilation, D, E, and F will become HA, HB, and HC. Does that make sense?
Yeah, because it's A, B, and C are reflections.
Yeah, that's right. So yeah, it's just a restatement of this reflection property. Okay, and then what's the other reflection property? The other reflection property is that when I reflect H not over the when I reflect H and not over the side, but rather when I reflect it over the point, the midpoint, then it becomes also this other point on the circumcircle, right? And so of course that comes from this parallelogram here, right? Maybe I don't know. I never know what to call it, but maybe we'll call it. Should give it a good name, maybe H A prime, I guess. H A prime, H B prime, H C prime. I don't want to call it prime because usually those are phantom points. So maybe we can call it not or something. Um, yeah, so HA not, HB not, and HC not. Okay, and so what is the key property? HA naught is this HA naught is the reflection of H over the point K. Okay, and so the second part of the claim is that these green points, these points K, L, and M are going to become HA naught, HB naught, and HC naught. So does that one make sense?
Yes.
Yeah. And then the final one is kind of okay. Then the red points will become A, B, C, and that's just because they were the midpoints to begin with. And so that and then okay then these are all concyclic, right? The ones after the dilation they're concyclic. They all lie on the circumcircle. So before the dilation they were also concyclic. Um, and that actually allows you to identify the center of the 9-point circle, because you know the whatever you know like
Yeah, the centers.
that's right.
Um,
Yeah, that's right.
is
Yeah.
H,
Sorry, say again.
is the center H or O?
Oh, you're saying the 9-point circle is centered at O? Kareem, I didn't understand what you said.
Um, yeah, because or no.
Yeah, so what we know is this dilation turns the 9-point circle into to the circumcircle. So we can say it like this. So this dilation, the 9-point circle becomes the circumcircle of ABC, right? When you apply the dilation. Um, so that tells you the center of the 9-point circle actually becomes O. So wherever the center of the 9-point circle is, when you dilate it around H by a factor of 2, it becomes O. So it tells you the center has to be the midpoint of HO. Does that make sense?
Yes.
And not only that, the radius is half of the circumradius. Okay. Um, yeah. Okay. So that's um, yeah. So that's some basics of the that's some basics of the 9-point circle. Okay. I'm not sure if I want to go over more. Yeah, I think that's enough theory for now. So yeah, any questions about this 9-point circle? Um,
No.
yeah.
Oh, but about dilation and velocity, should I study them from Evangelin's book, or are they not necessary, or should I just focus on solving more problems on the first two chapters?
Um, so um, you're asking about how to study about dilation?
Yeah, should I try to study it, or should I just use the time left to
So
solve
right. So
more problems?
yeah. So I think for so I guess yeah. So you have to decide what topics you want to study, but for geometry, um, at least you should definitely use Evan Chen's book, chapters 1 to 4, because that's part one of Evan Chen's book. Um, But let me just answer your question a little bit about dilations in particular, because this idea will actually appear in Evan Chen's book in these 4 chapters, I think in 3 instances. So there's, I think, three diagrams where you have this dilation. So one of them is the one we just saw. It's this 9-point circle. No, where did it go? I lost where it went. Um, uh, maybe it's here. I cannot find it. Maybe it's here. Yeah. So this is like, okay. This is maybe like the first dilation is the one that takes the 9-point circle to the circumcircle. Okay, so this is maybe the first instance. This is okay, um, factor 2 around h. Okay, and then there's the second very important dilation, which I think shows up in chapter 3. Okay, so this is in chapter 3. This one is also in chapter 3. Um, and this one is like this. It's um, the picture is you draw this medial triangle. So you draw um, the midpoints. These are the same as before. These are the midpoints. And now the picture here is, well, so first of all, okay, you when you draw these segments KLM, you get 4 similar triangles, right? So ALM, yeah. So what are the similar triangles? There's ALM, MKB, and LCK are all similar to ABC. And they're similar to KML. So there's an upside down one as well. Okay. So this picture, have you seen this picture?
Yes.
Okay. So now so there are some sort of uninteresting dilations. There's one that takes, KALM to ACB. Okay. That one's not so interesting. It's centered at A and it's a factor of 2. But at least it tells you some things like, this circle is tangent to this circle. Okay. So that one's not so interesting. But still, I mean, you should like, you should convince yourself that ALM, the circle ALM is tangent to ABC. That's true. You should convince yourself. Um, but the interesting dilation in this picture is the one that takes this circle to this circle. Do you know what its center is?
Wait, which circle to?
So it takes the upside down one, KLM, to ABC, right? Because these
Oh,
are
is it the centroid?
that's right, yeah. So it should be centered at the centroid. Um, let me rename the points correctly. B and C. Yeah, so that's right. So we have here and we have here. And I think the centroid is usually called G, I think. So it's called G. Um, G, I think, is for center of gravity. Okay, so that's right. So what is the one? It's centered at G. So it's centered at G, and the factor is -2. Okay, so it means um, Yeah, so it's centered at G with factor -2. That means whatever point you had, you stretch it by a factor of 2, but you move it to the other side. So you go from here to here. So does it make sense what I mean by factor of -2?
Yeah, I think you factored by two and uh, um, invert everything.
Yeah, you reflect around G. Um, I wouldn't call it inversion because invert actually means something else in geometry, but it's not that kind of
Uh,
invert. It's
okay,
yeah, it's just a
this
reflection.
is
Yeah. Um, so um, what are some things you can derive from this homothety? Well, you should read it in Evan Chen's book, but the main property here is that um, KLM and uh, I drew maybe I labeled them wrong. I want to label this one L and this one M. So this is L and this is M. So KLM and ABC have the same centroid. Uh, and that's one point. And then the other point is that the um, the the orthocenter of KLM equals the circumcenter of ABC. So do you see why this is true? I'm saying the orthocenter of KLM and the circumcenter of ABC are the same point. So do you see why that's true?
um,
So
oh
so
yeah,
yeah, right. So the orthocenter of KLM, you should take the altitude to LM. But of course, this LM and BC are parallel, so this is also the perpendicular bisector of BC. And so then it follows, right? Oh, yeah. Okay, so then I'll leave it as an exercise. What this shows is that actually H, G, O are collinear. So the centroid well, the common centroid, the orthocenter of ABC and the circumcenter of ABC are all collinear. And not only are they collinear, it tells you that um, HG equals twice OG. Okay, so this will be an exercise. Yeah, but it basically follows from these two facts. Um, and then this is all explained in Evan Chen's book. Um, yeah, and then there's a third homothety or dilation that's important. Um, so do you guys know what the third one is? We actually covered it last time.
oh yeah, the eccentric and eccentric.
That's right. Yeah. So so the picture there. Yeah, this is also a very important one. Maybe actually I have it saved. I believe
Yeah, I
it's
don't think it's necessary to explain it again.
okay. Great. Yeah. Okay. So I guess you
Yeah,
don't know.
I think I understood it,
Okay. Great. Yeah. So it's
but
but yeah. But maybe what I will do is fine. So I guess yeah. You understand this one. Maybe I'll there is right. So this one gives you a nice concurrence with collinearity with A, E, and X. There's Yeah, so there's AE and X are collinear. Yeah, so AEX collinear. There's actually a dual collinearity with the X center. So let me explain what that is. Which is, so how does AEX work? So X is just where the X center hits BC. And then what is E? E is you reflect D over the incenter. So you look at this diameter. Okay, so what is the dual collinearity? You say, okay, instead I now take X and I reflect this guy over here to Y. So this Y is so that this whole thing is so this Y is so that this guy is a diameter. Okay. And then what is the collinearity? Okay, maybe you can guess now. What should the collinearity be involving Y?
Y, no, wait, YDE, no, um, YDA,
That's right. It should be YDA. It should be this one here. Yeah, so that's YDA collinear because the homothency is centered at A and it takes D to Y. And there's a variety of things that are true, like I don't know, like for example, AE over EX equals AD over DY. Okay, there's infinite theorems you can generate, but yeah. So yeah, so this is also I think covered in Evan Chen's book, and he has some nice exercises about this. Yeah. Okay, so I guess that's it for today. Any questions about anything we covered or any of anything in general?
I don't have any questions.
Okay, great. So I talked to Sam, and then he said that you guys are traveling on July 14th. Is that right? Let me check. Oh, sorry. Let me stop.
Yes.
Let me stop recording.